Hello and welcome to this video where I'm going to show you how to use the noise adaptive filter features present in the DT6 to help clean up your signals that you get from taking regular data. So the first step you're going to want to do is take your sensors and place them where you want and then move it on this front panel. So in this case I have the green sensor here on the inboard of the motor and I have the blue sensor over here on the outboard of this kind of bearing output setup. So I'll just go ahead and move my sensors to match. So here we go. Then we're going to go click on modules and we'll toggle over to the noise adaptive filtering and we'll just click on that. And the first thing it's going to want you to do is take data. So I'll just take a quick 10-second reading of data and then it'll be potentially a little bit loud for a second. But once I'm done taking data, I'll turn the motor off and I'll explain a little bit further what exactly noise reduction we can get in this module. So go ahead and turn the motor on, get it to speed. Alright, so now that we've taken the data, we can go ahead and auto scale the FFT, and then we'll just match it. And what we see here is the top is where the FFT and the waveform were before we do any sort of noise reduction, and the bottom is going to be where it is after it does the noise filtering. So in the DT6 software in this module, there are two types of noise filtering. The first one we're going to go over is called self-filtering. So in self-filtering, the software will look at each reading and try and figure out which portion of the reading is actually noise and effectively try and reduce it. So here we can see that this is the blue is the vertical for the blue sensor and the green is the green sensor's vertical, excuse me. And we can toggle the channel up here. And if we look right now, we have self-filter chosen. So if we go ahead and zoom in kind of, let's see here, on the noise floor right here, and then we match the top, we can kind of see that the noise, especially in this high region right here, has actually been able to be brought down because the software has established that this region right here, these frequencies are largely noise, and it was able to bring them down. So that's how the self-filtering one works. It's useful if you have a machine that is particularly noisy or is in an environment where there seems to be a lot of electrical or mechanical noise, and if you want to be able to try and clean up the signal so you have more likely what are just the distinct vibration peaks, you can use the self-filtering. If I toggle it to reference filter, in this case, it'll take any vibration out of one channel that's present in the other. So in this case, I have the blue sensor set as my target and interference, and the blue sensor again is over here. And what that means is that I have told the software that the blue sensor has some target vibration that I'm interested in. In this case, it's the vibration present in this bearing, but it also has some interference potentially garbling up some of it. So in this case, the interference comes from the motor, and because they're so close together, most of the vibration I pick up in the blue sensor is actually going to be from the motor vibration over here and not actually the blue bearing vibration. So what I can do is I can tell the software that my blue sensor is some combination of the target vibration that I want and some interference, and the green sensor right here is at a location where it's pretty much only the interference that I'm talking about. And when I choose reference filter, what the software will do is choose any peak in the green that's present in the blue in this case and get rid of it. So if we go ahead and match here, we can see that this blue peak right here, right at 90 hertz, it figured out that, oh, there was a peak at 90 hertz in the green, and that must be causing this peak in the blue, so we'll just get rid of it. And so if we zoom in, we can actually see that here there was a peak at 90 or so hertz between both the blue and the green, and the software decided, oh, well, that must be from the green sensor, and therefore I'm going to get rid of it. So here, if we actually toggle off the green, we can actually see that it got rid of almost all of the effect of the the green sensor on the blue one, and so it's effectively gotten rid of this peak. And the same thing happens for a large part of the frequency range. We can see we have a bunch of these blue peaks up here that are actually harmonics of the motor speed, and when we choose the reference filter, it figures out that they were present in the green one and effectively removes them. So this blue peak disappeared, this blue peak disappeared, this blue peak disappeared, and any peak that it seems to find in the green one as a strong indication will be eliminated out of the blue one, as the software has determined that one of them is likely the cause of the other, or one of them is interfering and present in the other. And then if we choose reference and self filtering, it'll actually do both of the previous filters I talked about. So it'll self filter both of them, and then it'll reference filter, in this case, the blue one. And if I toggle this button, I can actually switch which one's which, but I'm going to leave it as the blue one because the blue one is the one I've chosen as my noise distribution. And when I hit return, I'll come back to this screen, and then if we hit acquire, we can go back to this screen and we can see that we have data here and here from these two as if we had just acquired it from the regular sensor. But now when we go to the analysis and we actually toggle those positions, we can actually see that this top one, in this case, which is where the blue sensor is, has almost all of the harmonics disappeared. See, all of these frequencies aren't even present in this signal. Whereas if we had taken this without doing any of those soda filtering, all of these peaks would be in here, and it would leave for kind of unusual looking waveform and would be hard to look at if we were trying to look for bearing problems in particular. We can also see it here on the time waveform. It got rid of most of the raw vibration and has left us with what is basically just the large impact events from our bearing, right? So it's useful for looking at vibration you know is particularly noisy or has some sort of interference involved, and you're trying to get rid of it to leave you with what is a best example of what vibration is really there. So I hope this helps. It's quite useful, and I think you'll enjoy using it.